Please join me in thanking the sponsors of the Fall 2017 and Spring 2018 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous anonymous sponsor. Please also join me in thanking the sponsor of tonight's lecture, PSW Jean Shaw, who is hiding in the audience somewhere, like right there. She is sponsoring the lecture in honor of her friend, Karen Shaner. Karen is a former White House advisor and adjunct professor at Georgetown University who worked in the astronaut program and is a fond and strong supporter of NASA and of manned space exploration. Thank you, Jean. I am pleased to announce that the following new members have been elected to the Society. Ashok Vaswani, a financier, formerly a partner at Bell Point Capital, now retired, interested in physics, who comes to us via the internet. Deborah Moy, a project director with Restaurant Consultants, interested in STEM education, space exploration, and environmental issues, who came to PSW through PSW Down Under member Frank Robert. Deborah's son Cameron is a student member who had the pleasure of meeting astronauts and physicists here before he took up his studies at the University of Maryland, where one of his professors was a speaker he met at PSW's LIGO program. I think there may be a family of in attendance tonight. Welcome, Deborah. Steve Lloyd, an adjunct college instructor and amateur astronomer interested in science generally, astronomy and volcanology, who comes to PSW through the Washington Post column Skywatch. Gary Dudinsky, an engineering manager with Orbital ATK, interested in satellites, and math, especially statistics, who comes to PSW through Meetup. Nathan Coleman, a software security engineer interested in evolutionary biology, astronomy, computer science, and anthropology, who comes to PSW also through Meetup. Alex Coleman, a student interested in computer science, natural language processing, machine learning, physics, and astronomy, who comes to PSW through his brother, Nathan. And tonight's speaker, Thomas Zurbuchen, whose interests will, of course, be apparent from tonight's lecture. Please join me in welcoming them all to the Society. If any of our new or recently announced members are here tonight and you do not pick up your signed reprint of Volume 1 of the PSW Bulletin, please see me afterwards and I will be happy to sign it and give it to you. James Heelan will now read the minutes of Chris Ralston's lecture at the 2388th meeting last month. James, podium is yours.
Thanks, Larry. Good evening. At the Cosmos Club in Washington, D.C., February 9th, 2018, President Larry Milstein called the 2388th meeting of the Society to order at 8:04 p.m. President Milstein announced the order of business, announced the evening's lecture would be live streamed on the internet, and welcomed new members. The minutes of the previous meeting were read and approved, after which President Milstein reviewed the 40th meeting of the Society held on February 1st, 1873. President Milstein then introduced the speaker for the evening, Christopher Ralston, professor of Northwest Semitic Languages and Literatures at the George Washington University. His lecture was titled, Cultural Heritage and Modern Inscriptional Forgeries in the Marketplace, the Intersection of Law, Ethics, and Biblical Studies. Ralston began by noting that since artifacts with inscriptions fetch higher prices on the antiquities market, epigraphic forgeries have become particularly troublesome. The ruling principle on epigraphic forgeries is that disproving authenticity is not that difficult, while proving authenticity is almost impossible. Forgeries purporting to use Northwest Semitic and Greek and Roman inscriptions have been produced for a long time. For example, in the late 1860s, a stela known as the Mesha stela, dating from the 9th century BCE, was found. The stela has an inscription in ancient Moabite, written in the Old Hebrew script. Shortly after that discovery, a man named Moses Shapira began selling thousands of similarly inscribed artifacts, which were even authenticated by a well-respected scholar at the time. These Shapira forgeries were subsequently revealed as fakes. Epigraphers use inscriptions on artifacts from legitimate excavations to study and to compare to inscriptions that appear on artifacts sold in the antiquities market, which often come from illegal excavations. One example of this is the Musayyaf Ostrakhan, which sold for $125,000. The artifact was initially celebrated and used as a basis for a scholarly reconstruction of the status of women in Iron Age Israel. Scholars eventually proved that this was a modern forgery, using comparisons with artifacts from legitimate excavations. In this case, the inscription's letters were accurately shaped, but their relative positioning was incorrect. Multiple other modern forgeries have since been revealed by the same means. Forgers have various motivations in addition to economics, such as sour grapes, as Rolston put it, and professional rivalry. Rolston noted that the forger of the Jesus Wife papyrus was a person who he said washed out of a Coptic studies program and likely delighted in his ability to dupe world-renowned scholars. Many forgeries are also pranks. For example, the Philistine Hebron inscriptions were authenticated by a well-regarded University of Michigan scholar in the late 1960s. Years later, an Israeli scholar revealed the inscription to be an apparent joke, as it is the same text as a famous authentic inscription, but written backwards. Some forgers are also motivated by professional or personal aggrandizement, since publishing an artifact with scintillating content draws significant attention. For example, one of the highest profile epigraphic forgeries in the last 20 years is the Yaakov ossuary, initially valued at $2 million. The ossuary itself is an authentic bone box, but is the inscription, which translated into English reads, Jacob, the son of Joseph, the brother of Jesus, that is suspect. Rolston pointed to the difference in the incision depth, clarity, and kerning between its two parts, contending that the part that says, Jacob, the son of Joseph, is authentic, and the part, the brother of Jesus, is a modern forgery. Religion and politics may also motivate forgers. For example, the Jerusalem papyrus garnered international attention in October 2016, purporting to be a rare ancient reference to the city. Carbon-14 testing dated the papyrus to 800 to 300 BCE. Rolston said, however, that ancient papyrus is easy to obtain, and faking ancient ink is also possible if the forger uses the carbonized remains of unearthed ancient beans. Ultimately, scholars determined that the Jerusalem papyrus was a forgery because it contains a basic grammatical error that a speaker of ancient Hebrew would never have made. Whatever their motivations, forgers are producing better forgeries, and Rolston suggested that scholars must work together to detect modern forgeries through orthographic, paleographic, and other means. To assist in this process, Rolston recommended that all artifacts from the antiquities market be flagged as such to indicate their lack of authenticated provenance. He also recommended that scholars not base any of their works on these artifacts because they are so often compromised. Rolston further recommended categorizing the inscriptions from these artifacts based upon their likelihood of authenticity. President Milstein then invited questions from the audience. One guest asked whether the inevitable arrival of the, quote, perfect forgery will end the antiquities market. Rolston said, the perfect forgery is coming, but that while forgers are becoming better at forging substance, they're still committing basic errors, such as the grammatical error in the Jerusalem papyrus. Nevertheless, to avoid educating forgers, Rolston does not reveal all the techniques he uses to unmask modern forgeries. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:02 p.m., President Milstein adjourned the 2,388th meeting of the Society to the social hour. Temperature, 4.5 C. Weather, cloudy. Attendance, 62. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any comments on, corrections to, or additions as to the minutes? If not, I will entertain a motion from a member to accept the minutes as read. I have a motion here. Do I have a second? I have a second. All members in favor? All members opposed? No one? Okay. Minutes are accepted as read and will be posted to the website in due course. We will now turn to tonight's lecture on eclipses, using shadows to shed new light. It is my pleasure to introduce tonight's speaker, Thomas Zurbuchen. Thomas is the Associate Administrator for the Science Mission Directorate at the National Aeronautics and Space Administration in Washington, D.C. Previously, he was a professor of space science and aerospace engineering at the University of Michigan in Ann Arbor, and he was the university's founding director of the Center for Entrepreneurship in the College of Engineering. Tom's research is focused on solar and heliospheric physics, experimental space research, space systems, and innovation and entrepreneurship. He has been involved in a variety of NASA science missions, including Ulysses Messenger Wind, the Advanced Composition Explorer, ACE, and the Solar Orbiter. He has been a member of 2 standing committees of the National Academy of Sciences and has served on numerous science and technology definition teams. Tom received the National Science and Technology Council Presidential Early Career Award for Scientists and Engineers, and he is the recipient of 4 NASA Group Achievement Awards. He is sole lead or co-author on more than 200 technical articles in refereed journals. Tom earned an MS and PhD in physics at the University of Bern in Switzerland. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Thomas to the podium. And I apologize for saying Tom.
No problem.
Let's see if I can get you up.
Just want to make sure this is on, right? So all I can think of, I wish I was here for the last talk, because it sounded really interesting, and whoever wrote that summary just did an amazing job. I wish I heard it. So what I want to talk to you about is really about some of the science that we're doing at NASA. And I want to talk to you about both a practitioner of science, somebody who believes that doing science really teaches you more about yourself and the world in a way that profoundly affects you. But it also a practitioner of science and a leader of science now in one of the proudest programs anywhere in the world, and really related to how we not only increase what we know about nature, but sometimes actually change how we think about ourselves. That, by the way, is why I studied physics and astrophysics eventually, because I thought the power of science to do that is just amazing. The fact that we think differently today because of the things that we found here, things that we found sometimes in the most surprising areas. And you're going to see the element of surprise popping up here and there in some of the stories I'm going to tell you. The way I'm going to do this, actually, is to focus on 3 stories. And they have something in common, and that is that they teach us science not from light, but the absence of light. Of course, I stumbled onto this story because of the first one, the first story I'm going to talk to you about, which is the great solar eclipse of 2017. I'm going to tell you about that and kind of what we learned from it. Many of the publications are still being worked on right now. A lot is being discovered right now. I'm also going to talk to you about using eclipses to explore the outer solar system. One of these stories actually will lead to its final highlight only at the end of this year. I'm going to tell you about this. And then the third one is perhaps one of the most profound stories, one of the stories that has precisely the promise that I talked to you about. So it's a promise to not only teach us more about nature, but perhaps let us change how we think about ourselves. And it's about eclipses in other solar systems. So it's really 3 stories that I'm going to tell you about. And I hope you'll enjoy them just as much as I do, because whenever we talk about science and we start going deeper and deeper, it becomes more and more amazing and surprising and exciting. So I hope that's what you get from it. All right, so I want to talk about the first story, which is the great solar eclipse of 2017. Of course, what you see here is are pictures of that eclipse taken actually by an expedition by the National Geographic, and you see the various phases of the eclipse. And if you've ever done this, it's kind of one of those experiences where the last 1% is 99% of the experience. So you see the sun, it's very, very bright. You still can't look at it. You use these very dark glasses, and all of a sudden, something happens, and a totally new world shows up. The atmosphere of the sun, the atmosphere of our star, the magnetic atmosphere of our star, which is actually the source of our space environment, the source of space weather. Now, if we lived in caves and we didn't have electricity or satellites, if we didn't have iPhones in our pockets that talk to these satellites and use these data, we wouldn't care about space weather so much, because all it would show us every once in a while is a beautiful aurora. Because of these systems, though, we care about space weather and the influences that come from the atmosphere of our star. And we not only want to care about it, we want to predict those. And actually, much of these perturbations come from a place that we don't usually see, which is the corona, the atmosphere of our sun that we're seeing during the eclipse. So how did I see the eclipse? Well, that's how. So one of the good things about the job I currently have, I get to sit on planes. We have in NASA science mission, directed 25 airplanes. This is one of them, so we do a lot of science, both atmospheric and other type of science. And I sat there on a Gulf Stream and looked out the window. The day before, we did exactly the same kind of flight. And of course, what happened is the sea was very beautiful, and all of the land was full of clouds. So if you were in Oregon, which is off the coast of Oregon, you would have been really nervous the day before. And so one of our really supportive congressmen, I'm not going to tell you which one, but send me a text and say, hey, I need the best weather prediction person. I need to know where I need to drive so I can see the eclipse tomorrow and say, stay where you are. You're going to be just fine. Anyway, so the next day, we came out, and of course, I'm looking out the window. Next to me is the NASA administrator. And you should know, when I looked out that window, I saw a total eclipse for the first time in my life after I've worked on the physics of the solar corona for close to 20 years. And so for me, that moment was really exciting. I looked out there and, I was sharing it with my colleague, my boss, in fact, the administrator, who basically told me at the end of that day, and he's repeated it ever since, that this day was one of the top 5 of his entire career in NASA, because it meant so much to him to see the excitement of science right there. Yes, there's many things we do that are amazing. I was just attending this launch of this new weather satellite that's going to provide weather forecasts over the west coast of the United States. That launched just last week. And so we do amazing things. We walk out in space. These humans do amazing feats, but, observing nature is one of those things that is hard to match, frankly. And so we were there. So if you look out the left, so the sun is on the right, or you look out the left, what you see is this shadow coming over the cloud. See, during the eclipse day, all the clouds were over the water, and the sky was wide open over land. You see that shadow going over us. You see the wing of the airplane basically being dark, because all of a sudden it went away. Everything was really amazingly quiet and calm. And then the shadow left and went over us, and you see how we're crossing over land over there. So for me, by the way, we had that idea when we looked out. I said, let's put the GoPro out this side, because this is going to be amazing. This had millions of views on Twitter after I posted it, because I think it's just so amazing to see that. Of course, we had many different views. This was taken by Peggy, our astronaut who broke every record, every US record in space, taken out the space station. And we also see there the darkness, that shadow cone going over land, and of course from the moon. So right there by the moon we have a spacecraft called the Lunar Reconnaissance Orbiter, LRO, and it looked over the shoulder of the moon, if you want, towards the Earth. And of course what you see is right there over the United States, that dark shadow, the very shadow that I saw when it went over the coast there. You see the clouds just at the end of the coast, the clouds that you saw the shadow going over. So that's cool. That's really amazing. But what's really great about this is that actually we learned a lot about the sun. This is the same eclipse observed from a telescope, a Hinode, actually a Japanese NASA-built telescope that is looking at the sun in X-ray. Do you see those bright spots? If I looked at those bright spots, they're really bright in X-ray. So they're really hot, right? X-ray is hot. So they're really bright. So these magnetic fields that are there in these spots are really strong magnetic fields. And the sun underneath it is stirring like a pot of oil. And the magnetic fields are driven into each other at a way that all of a sudden the energy in that magnetic field, which by the way is the dominant energy in that atmosphere of the sun, something we never see otherwise, turns into that heat that lights up the atmosphere so much that it comes bright in X-ray. And so that's what we see here in this as the shadow again goes over it. Now, that very atmosphere can be observed by our spacecraft in a multitudes of ways, and we can look at it in many different temperatures, all the way from 10,000 degrees to 1,000,000 degrees. As opposed to anything that we see on Earth here, really, the sun surface is about 10,000 degrees, and its atmosphere is 1,000,000 degrees. So think of walking into a kitchen, you have a pot on a stove. So imagine, usually the water in the stove, as you know, is cooler than the stove itself. Well, the sun is different. So the sun is that the stove, if you want, is 10,000 degrees in round numbers. It's 6,000 or so. And the atmosphere, the thing on top, is 1,000,000. So it's exactly opposite of what you would think. Why? Because of that magnetic field. So if we want to understand space weather, if we want to make predictions, we need to understand how that magnetic field couples into that atmosphere. And of course, we have calculations. In fact, that's a calculation we did the day before using observations from NASA that we had seen downloaded that day, and we used NASA's supercomputer at NASA Ames to actually run the calculation of this. And you see these arcs. These arcs are magnetic field, just like, so if this was the Earth, and I showed it, the Earth, you would see these kind of, just a dipole, arcs that go this way. Well, so it looks a little bit like a dipole, so it has this belly, but it has multiple bellies, including some of these smaller arcs, which, remember, I already talked to you about. Those are the hot ones that you saw in X-ray. And so basically, this model basically said, when you see the eclipse, you should see these magnetic arcs standing out. So it's become a really great test case for the very models that we're using, actually, to make space weather forecast, and we're transitioning to NOAA for operational use. And so basically, what happened, of course, we have these data that we can produce. So we actually make, in this case, fake data from the model that basically says, look, here's the magnetic field, here's how the X-ray will look. It looks a little bit similar to what you already saw, right? And here's what the brightness and the polarized brightness will look. So in other words, what you will see during the eclipse is the picture from your side, the very right. Okay, so how did it work out? Well, what you see here is an observation that was made actually in a really unique fashion. So it's an observation that was made by 20 high schools using telescopes all over the line of totality. See what happened because of the fact that this eclipse went from coast to coast for the first time ever since we're actually doing this. We could stitch together multiple observations over close to an hour of duration of that innermost part of the sun we actually don't have airplanes that are fast enough. You could probably fly one. There's a pilot there, I know, a Navy pilot. So there's, one or two airplanes that are fast enough, but our NASA airplanes are not. So basically the closest we could get is two airplanes at nearly Mach 1, and they basically hand it off if you want the observation. So we flew behind each other. That's the best we could do. But these are school kids on the ground, and they would do the best observations. Remember these arcs I talked to you about? You see them. Do you see kind of how they're hanging out? This is that same observation actually put together with space observations. The reason I did that is to make a simple point. This is actually hard to observe, even from space. And so basically what these school kids did, together with professional guidance, of course, so not on their own, but what they did is actually made observations that are really, really critical and that are now in our publications. And so basically what you see is the ultimate result here. What you see at the top is the observation done by one of our teams at NASA. The observation by one of our teams at NASA together with the model. And we could talk another hour about this. I will spare you that. But basically you see some of the large-scale structures are right there. Very well produced. Some of the others, the smaller ones, some of the beams there, not so much. So we're learning a lot about this. We feel really good about the model in general, and we feel really good about this test. And together with so many such experiments over time of history, we learned something new about science during this eclipse. Not from light, but the absence of light, which is what this really is about. That's story number one. All right, let's launch into the second story. It's really using eclipses to explore the outer solar system. And I'm going to talk about a mission. Who is it? Where are you, Kirby? That's what he's working on, so he should come up here and tell the story. And but basically, it's a mission called New Horizons. In fact, I'm told that Alan Stern was here giving a talk to this esteemed group not too long ago. He's an amazing colleague and friend. And I'm just so proud of his team and just the science that he achieved. And of course, we all know, on Valentine's Day, we give cards. Well, the nerds among us give cards to our loved ones with the heart on it of Pluto that you see right now. Pluto, which was many people thought was a really boring body. There were a lot of scientists in the planetary community that were actually less than excited that we would spend about $1 billion of a spacecraft to go out there. Of course, that was almost a miracle to do that because so many of the missions that go that far away from the sun are 2 to 3 times the cost than $1 billion. And so much innovation that Alan told you about got us there. Alan told you about the excitement of looking at these lakes that are full of nitrogen, really filling in craters that are there. The fact that it's a lot flatter than we thought, so it's not just a Swiss cheese with a lot of holes in it, and basically tells us about the amazing history of this planet. All this stuff he would talk to you about. He also, of course, would talk to you about the atmosphere. Well, one of the amazing parts, and the reason we wanted to, of course, observe Pluto during that time is during its highly eccentric orbit. If Pluto is far, far away from the sun, kind of at the long side of the ellipse, right? The atmosphere freezes out, so there's not much fun in the atmospheric sciences. On this side, though, when we're close, the atmosphere is right there, and you look at this, it's like, is this really Pluto? It looks like, a snowy landscape or so, so the atmospheric science of it is really exciting. Of course, we learned basically 90% of what we know about this planet during this flyby, but I wanted to talk to you about how we learned about this, actually used not only our understanding ahead of that flyby, but also how we actually targeted the spacecraft just the right way, using shadows from far, far out. So this is ahead of the encounter, looking ahead of Pluto, and basically shows, of course, the occultation that is there. But what I want to talk to you about is the concept of occultation. So what you see, and perhaps Alan talked to you about, I wasn't at that particular meeting, but basically what happens is there's a lot of stars out there, right? Go look at them. Every once in a while, if you were really patient and you had good eyes, a star would blink. Why? It's because an object goes in front of it. And it will blink and come back. I'm going to show you an example of that. It goes away and comes. Well, so what happened is because of the fact that we knew approximately where Pluto is, we knew well ahead of us getting there that the shadow, Pluto's shadow, would go over a specific part of the ocean. Now here's the problem. It's the ocean. We don't usually build telescopes on oceans, right? So we have telescopes, in Hawaii, Tenerife, good vacation places, in other words. No, it's actually very specific reasons why telescopes are there, because of the seeing, as they say, because the night sky is very calm, very little turbulence. So the question is, how do we catch that shadow? If we caught that shadow, we did it well. There's a number of things we would know. Because we know where the star is exactly, we actually would know much better actually where Pluto is. That argument is not so strong here than with the other object I'm going to talk to you about in just a minute. But we know better about the locations. We actually also know, because of the fact that, remember I talked to you, there's an atmosphere. If light goes around an atmosphere, the atmosphere behaves a little bit like a lens. So we could actually go look at that lensing effect from that atmosphere, because light goes around and gets focused. We could learn from that about the atmosphere and basically actually make sure, for example, that there's no debris, kind of rocks around that could be a hazard to the spacecraft. Those were the objectives. Well, how did we do it? We used one of the assets that we have, which is called SOFIA. It's basically, I laughingly refer to it as a 747 with a garage door in it. So it's basically in the back there, you see, is basically a 2.5 meter mirror that is basically mounted on the inside of a 747, and it's a highly sophisticated machine. It's, of course, we have literally a door that opens at high altitude. We open it. And in addition to that, though, the one thing you don't see, the way you should think about this, is actually an airplane that flies around a telescope. It's not an airplane that carries a telescope. So the telescope is absolutely steady in the sky, absolutely rock solid, and the airplane flies around it. And the mechanisms control, a sophisticated control mechanism. Anybody in engineering, really gets geeked out about it. It's so exciting and enabling for this particular telescope. So what we did in 2011, years ahead of the flyby, we actually flew from New Zealand over the ocean for a whole night and did kind of a zigzag type of analysis. What's really interesting, you see the various edges here? What actually happened is after this airplane took off, there were data that came in from a new spacecraft from Europe that actually gave better coordinates for the star that we want to use. There's a spacecraft called Gaia, and better coordinates came there. Calculations were updated, and actually the airplane trajectory was adjusted to include all these data. So in fact, what we saw is the very occultation that I just told you about. So what you see is that star disappearing behind the rock called Pluto and coming out from behind. And so you basically see star shines, turns off, back up, and it is steady. The Pluto, that the obstacle went away. The occultation is over. You see that flash? That's what I told about, right? Kind of the fact that just like when you look at the atmosphere, the light gets spent, that very bending of light tells us about this atmosphere, and the publication that carried this particular figure talked about this analysis. Of course, once we flew by this amazing object, we learned a lot more, but this is a way we learned about this particular occultation, and we learned about Pluto. Now it's interesting, we flew by Pluto with New Horizons, And the question is, what now? Of course, eventually the mission is over, right? But, Alan and his ingenuity is basically, hey, let's go somewhere else. So what we did is we actually used the Hubble Space Telescope and other mechanisms to look whether there are small objects out there in the outer solar system. Remember, Pluto is really far away, right? Far beyond the big planets, like, Jupiter, Saturn. And they're out there, there's these bodies, they're called Kuiper Belt objects. These bodies are really interesting because they're kind of left over from the beginning of the solar system. When the solar system came together, we know, looking at all these other solar systems in the universe, we know that there's a big gravel yard out there, and there's a process that's called accretion that starts happening when these rocks, these gravel pieces start interacting with each other. Some of them get clumped together, and eventually some of the bigger clumps turn to planets. Some of them, depending on when they are, where they are, and so forth, they turn to bigger, smaller, rocky, more gaseous planets, and so forth. And so that process has left pieces out there, a whole bunch of tens of thousands of pieces of these Kuiper Belt objects that are out there. And believe it or not, there's a piece discovered in 2014 called MU69 that was just about where New Horizons was going anyway. Remember, we flew by Pluto, and just almost where we wanted to go was this piece. Now, remember, I told you there's two issues we want to be sure about. A, where is this thing? Because we saw, actually, I did not bring the picture from the Hubble Space Telescope, an amazing science machine. I didn't bring the picture of the Hubble Space Telescope because it was so unimpressive. It's basically a fuzzy picture, right? And we knew that it is a really good picture because that object behaved like it should. Remember, it's still in orbit, so it moves. We kind of learned where it was approximately, but not nearly close enough to actually know where we are exactly. So are we going to fly by at 10,000 kilometers? Are we going to fly back at 5,000 or 50,000, right? So these kind of uncertainties were with us. Also told you, remember? So I want to know where it is. I also want to know whether there's debris fields out there. The same way as with Pluto, I want to be sure that it's safe. So remember that trick with Pluto, which is to go find the shadow. Well, okay. Only problem is the shadows are tiny. The other problem is these things are far, far out. And so the shadows are so quick that if you looked at the star, it took like a second or 1.5 seconds for the star to turn on and off. Also, if you just went over a few miles, you did not see that shadow because the object is so tiny, right? It's not Pluto. I mean, Pluto is not a ginormous planet, but it's a lot bigger than the little Kuiper Belt pieces out there. Of course, the only reason I'm telling you this story is because the amazing thing happened. We found the shadow. Now, I did bring the Hubble Space Discovery. Do you see these fuzzy things? They move, right? So you know, wow, it's an object. So it's not some broken pixel, right, in the camera. So it's an object. They move, and it's frankly, it's an object. We don't know much about these Kuiper Belt objects. We've never seen one up front and personal. We think some of these moons that are in these giant planets are actually objects like that, but we've never seen it kind of in their natural habitat out there in the Kuiper Belt. So basically, so that's basically what we saw. Okay, now remember, we want to figure out, is there a star somewhere that could cast a shadow? The answer is yes, 3 times. Found a star 3 times. Now with Gaia, we actually know much better where these things are. But frankly, the uncertainty, is really high. Do you see there's South America, there's Africa. Do you see how the shadow, this kind of really quick shadow goes over the entire world in a matter of minutes, right? And kind of you stand in place, it's in a second, it's gone, right? So it's going in there, out the other side. Then there's some other passes, some of them entirely over the ocean. Frankly, it's even hard to get there with a 747, right? Because you have to fly there. And we don't fuel in the air like you may, sir. So But, like we have to fly there, do the observation, then go back to, hopefully not on fumes. So, and then another flyby like this. And so here's what happened is our friend Alan, I remember I saw that purchase order. Let's go buy 40 telescopes. It's like, why? From New Horizons, I think that's the number, 40. Perhaps it was even 50, I forgot. You're there? All right, where are you? On top. On the right. Anyway, so you should be up here telling the story. Anyway, so the point is for me, like frankly, I took my team and basically say, okay, look, I think at NASA we should do some things that sound a little bit crazy. Because if we're not doing them, who is, right? I mean, we're an organization that wants to lead the world. We set the speed of discovery in the world when it comes to science from space. So we need to go, and I was really supportive from the beginning, but I told my friends, the likelihood of them seeing that shadow, not so big. Because, like, math too. You write it down, and you basically, it's not so big. Well, but the way you do this, and, Alan and his team, basically said, well, the way you beat this is with crowds. Remember I talked to you about citizen science already with the solar eclipse. This is another one of, actually many of them were professional scientists. But the point is, what you have to do is go catch that shadow. Now the first one, remember I told you, was in South America. So first of all, it's the capital of the wind. So, I mean, I don't know, have you ever tried to set up a telescope in the wind? Not so much, right? It's really, really hard. Anyway, and then you see the snow. Some of it's just horrendous weather, and frankly, the whole event went over, and null result, right? Is that how you do? The first two. Yeah. So a null result until first two was nothing, and then all of a sudden, I got this in my email from Alan. See that? Because that was from the third time that all of a sudden that very star, that's a star that will never be known for anything other than this, right? It's a star that happened to be behind the favorite object that we found because New Horizons happened to be on the way. That star turned off. What's more important, though, it didn't just turn off once. It turned off 5 times in telescopes that were next to each other. And so not only did we know, because of the location of the star, where this thing is, we actually got information about the shape. Now, what's surprising about the shape is it seems to be elongated. So it's not a spherical thing. By the way, not too surprising. In the following sense, whenever things are not heavy enough, they don't go to their lowest energy state, right? So you with lower mass type of objects that don't have the evolutionary history as the Earth or some of these other things, they don't necessarily are round. Actually, we look at the asteroid belt, they go up to 3-to-1 type of ratio in terms of, the skinniest to the longest. So this one either could be a potato like this, but it could also be that there's actually 2 objects. So we don't know. What we know about this object now is basically everything other than the location and some of the analysis from ground-based telescopes with a few pixels of data is what we know now. But what's really exciting? We're going to learn about this on New Year's Day 2019. By the way, that's what we're doing, honey. When this New Horizons is flying by these objects, and the one thing I'm going to tell you, it's going to be different than we expect. Remember, that's the one thing that I've learned so far. Our expectations are usually not as amazing as nature. Nature tends to really surprise us, and pretty much every time in a positive fashion, in a way that is more rich, more exciting, more interesting, and very different than we expect. So that's the end of that story. Remember, end of the year, that's where you want to hang out and then look at the state of these objects. Is it 1, is it 2? We don't know. All right, so that's the second story. What I want to talk about now is the third story, which has to do with eclipses in other solar systems. And with that, I want to start in the inner solar system. And what this is an observation of Venus. Actually, it's an observation of the sun. It's an observation of the sun in ultraviolet. Remember, you see, now you're an expert, right? You see these arcs, so they're magnetic fields, they're sunspot underneath it that are storing the path. You see kind of the radiation that comes from there, and you see that circle. It's multiple instances. You see the circle going through, and of course, it's Venus inching in front of the camera that's hanging out at the Earth. Now that object that's happening all the time. If you're in the right plane, you know, if the thing goes in a different plane, for example, if it's a bigger or a smaller object, there are the radiation of the sun. If you just start with a really good measurement device, the radiation of the sun in that transit technique is going down ever so slightly because of the fact that it was shaded, if you want, by that little body going in front of it. So what's really exciting about this is that technique actually is really useful. Here's your favorite object. So that technique is really useful in some of the stars. I'm going to ask you a question in a minute. In some of the stars out there, there's this TRAPPIST star that, by the way, is a star that was observed initially by a Belgium telescope from the ground. They saw some of them. I'm going to ask you what this is. Ready? See the peaks up. I'm going to talk about the peaks down, but I'm going to ask you what the peaks up are. Keep that thought. So anyway, so you see these like the observation was done from the ground-based thing, and we used our Spitzer telescope to look up there and stare at this object for a few days. And you see all these things coming down. So what we know from this, and it's so repeatable that we actually learn which one of the little, deflections belongs to which one. So we know how to label it over the 20 days or so that the observation occurs. What's exciting about it is because of the fact that there's more than one of these. See, remember gravity, how it works. Of course, the reason they're in orbit is because their star pulls them in. In this case, it's a really small star. It's a cold star. And so basically, it's pulling them in. What's also interesting, though, because there's multiple of those, the planets, they actually tug on each other as well. And so what happens, if I compare B and D next to each other, or C and F next to each other, ever so slightly, they are tugging on each other, and they're ever so slightly deflecting from the just regular clockwork version that would happen if these planets are not interacting with each other. So because of that, because of the fact that it's the mass that pulls on the planets relative to each other, just because gravity works like gravity works, we can actually learn about, from the from the overall amplitude of this, we know the size, we can learn about the density of these little planets. We also learn about where they are. So it's not that hard a calculation to just really derive from this. It's kind of, it would probably take me like 5 hours in a classroom to really do the whole thing, but it's not a whole semester, to get my point, right? It's really just simple physics that is happening. What we can get from this is, from this entire observation, is the fact that this is a system with 1, 2, 3, 4, 5, 6, 7 objects, 3 of which are at the distance from everything we know in terms of total kind of behavior in radiation, are at a location where water can pool on the surface. So that object with all these things is up to that point, was a record breaker. Because not only did it have the most planets at that moment, by the way, it was speed already, but it also had 3 objects in the potential habitable zone. That's such an approximation because we don't know enough about these things, but just from this calculation, just doing a temperature calculation that you would do in a physics class, we know that the temperature is such that water could be above freezing, below the boiling point. So I tell you, this is a personal story about this thing. So this was the first big press conference that I did. By the way, it came to me, and NASA has processes to define whether a story is good enough that we should make a process. It's like, I don't need a process for that. Let's go do it, right? This is an amazing story. And I had just moved to NASA a few months earlier, and I lived right next to the museum. So we did the press conference, and I walked in the morning by the newspaper title pages. You've seen them out there. And well over half of them had this on their title page and above the fold, including the New York Times and many of the newspapers you've seen, Wall Street Journal. It was there on the title page. And it talked to us about the amazing power of these eclipses, the absence of light, to teach us about worlds that keep us up at night, frankly. Because those are worlds that in many ways, they're different than ours. Remember the scale? They're so small that they could fit right on the inside of Mercury. By the way, why is the temperature right then out there? Well, it's because the star is so wimpy, right? It doesn't put a lot of energy out. So basically the star is so faint that out there is the same temperature approximately as where we are at Earth. And so we learn about these worlds in a way that wants us just to know more about it. So for me, by the way, within the first week, we had 3.2 billion downloads of our web content we put up there. And it's literally one of the biggest stories we've ever done at NASA, because not just because of what we learned about it, it's the promise of the story for more. Because since we started thinking about ourselves as humans, we asked these questions: are there other worlds out there like ours? And those hints from those data are just so amazing that it literally was around the world one of the biggest science stories of that particular year. Okay, what was the peaks? Any idea? Anybody? So I talked to you the eclipses, but then there were some peaks. What are they? Yeah, exactly right. Remember I told you at the sun, these things there's really bright spots at the top of it. And some of these bright spots are actually pretty quick. These emissions, they're the very emissions that are there. So these flares actually also occur at these very wimpy stars, the red stars that are there. So we observed those too. And actually there's work on this as well as atmospheric modeling work done so often by atmospheric scientists that often do work on Earth using the very same atmospheric models that are there. All right. So, of course, we want to know more. So I want to tell you about a little bit is kind of where we're going with this. And so what we're doing. This is brand new stuff that we're working on. And of course, what we want to do is really learn about something disappeared here. Nobody move. What we want to do is learn about the various worlds and learn how to interpret the various worlds, kind of the atmospheres that are out there. For example, Earth, Mars, and Venus. Venus, of course, has a lot of CO2. So does Mars, and the Earth has more oxygen, but also, methane. So each one of those gases has specific emissions. If we look from the outside, this is what we would see. And what we really like to do is see a whole bunch of lines of atmospheric emissions, because we would look at certain emissions and say, hey, that looks a little bit like we think the ancient world looked when certain gases like oxygen and ozone were produced by living organisms. There's certain things, of course, You always hope like they have factories there and they go on break, at 4 o'clock local time, so, the gases go down. In the absence of that, just natural kind of emissions, there's tremendous signatures that would indicate vegetation being there, certain water vapor, geologic activities, and many more. So we've never seen anything like this. This is a model. We've never seen anything like this. Well, how could we get there? So first of all, we're trying really hard to get this thing to launch, and I'll feel a lot better once it's deployed at L2 and ready to go. I just got a picture today, for the first time in history, all the parts of the telescope are in one and the same room. So we actually, yeah. This picture, of course, was done in the neighborhood at your workplace at the NASA Goddard, where this amazing telescope was put together and tested and shaken, and sound was put at it. Really harsh testing before it was shipped to NASA Johnson. And kind of what we have a joke, and we don't say it too low, but wherever the telescope is, there's a natural disaster. So here we had the worst winter storm, right? Kind of, and by the way, the teams were just amazing in every single case. Then we went down to Houston. You remember what happened there? Harvey came and dumped so many feet of water, actually, and the telescope never knew that there was a storm on the outside, because the team did exactly what they're supposed to do. Many of them had tremendous impact to their house, to their livelihood, and they were working with this telescope, getting it through tests clean. We have no worries about this telescope. And it's now meeting up with a bus, with a spacecraft that is not shown here, that is one of the biggest buses I've ever seen. I go look at it, you look at it and you're impressed. That's basically one way to think about it. It's 4 thermal protection shields that are the area of a tennis court, that are basically as thin as an aluminum foil in your kitchen, or thinner actually, that are being deployed in space. And so that's what we're putting together, running it through tests, and then eventually in 2019, hopefully getting it on a rocket and launching it into space. And then it will be 6 months. The 7 minutes of terror they always talk about, entry, descent, and landing of Mars. This is 6 months of terror until everything is set up, the telescope is set up, and it can do the very observations that I want to do. Because of the fact that there's some of these planets at these cold stars, this actually happens to be the best tool. By the way, the good, amazing colleagues who came up with the Webb would have never dreamt that there's so much excitement about these stars, because we didn't know about these planets being there that are now at the center of so much research all around the world, but especially in the United States. So we can't wait to get this out there. So we'll make a lot of progress there, but we're not done. What we really like to do is create an eclipse that's a lot better, and we can put an eclipse that we can put on every single star we want to. See, the problem that we really have is, go to a football game, to the outside you have the floodlight there, and imagine you want to observe the exact motion of a fire bug, like one of those lightning bugs right next to it. You don't see it, right? Because your eye is overwhelmed by the floodlight. Well, that's the picture. You have a massive star that's emitting so much more light than the little planets. And we're interested in the star too, but much more interested in the planet next to it. And so what we'd like to do is do this. Like right in front of the telescope, perhaps on the inside of the telescope, we want to shade the star. That's called an internal occulter or a coronagraph. Actually, there's work going on right here, both at Goddard, at the Space Telescope Science Institute, that some of you may know about, but also at the West Coast and elsewhere about these internal occulters. So that's one way. It turns out there's certain limitations about this. Because see, light scatters. So like you can take a razor sharp edge, there's still a little bit of light that comes off it. And that's the limitation of that. What we'd really like to do is make our artificial star. So imagine we have a telescope, just like the Webb, and something like 10,000 kilometers towards the star that we want to observe, somewhere, flies a flowery thing. Now, why is it and then it occults the star. Why is it shaped like this? Well, it's shaped like that because, remember, light is made out of waves. And so this is precisely the right shape that the light that's coming around the corner just nulls itself out right at the center. So, I mean, this is not 5 hours of math. It's a lot more of math, and invented by a professor at the University of Colorado who came up with that concept, the star-shaped concept. I always say, I actually think there's going to be more inventions here. I actually am not sure that we've invented the kind of the magic tool yet. There's multiple tools that are going to be there for multiple applications, and there's much yet to be invented. But what we're trying to do, what the community is trying to do, is invent these occulters, artificial eclipses, because we can't wait to actually look at things, at systems that are just like our sun. You know, something like our sun, and next to it we know are planets, or do we? Well, before I talk about that, I just want to tell you how much technology goes into it. We have to make these, and actually there's a lot of technology development that looks a little bit like an origami, right? You want to deploy this thing, and then, by the way, it needs to be deployed at an accuracy of a fraction of an inch out there for this to actually work the right way. We're not done with this yet. We don't know yet how it works exactly. Remember, it can't flex either. It has to be exactly planar. And so this is one of those things we're working on. But why are we doing it? Because we want to learn from the absence of light, not from the light itself, from the absence of light, because it takes away the thing that distorts us from actually observing the thing we want to see. What we saw from the Kepler spacecraft is, I would say, an avalanche of planets. We learned about stellar systems in a way we would have never guessed. See, I did my PhD in '96 in astrophysics, and I remember the day the first planet outside of the solar system was announced. It was announced in Rome in a conference. And I remember because I was a grad student in Switzerland. You said that in your introduction. And there's this professor from Colorado showed up with his Birkenstocks, and I got the task to walk him up and down the mountain. I was like, are you sure you want to wear those shoes? He's like, he's fine. Anyway, so I walked him up and down the mountain, a nice path. But what really was amazing, like he stopped everybody he met and say, translate. We just discovered the first planet on the outside of the solar system. So I was telling all these people, it's like, he's American, it's okay. Anyway, so I'm 2 now, so anyway, so get off the, so that's how, I remember that day so clearly. Well, that was the first observation, or it was actually 2 in that first discovery. And we have thousands now. We have these orbital periods. A lot of these theories and models about planetary formation have died because we actually learned about many other systems. So when we go from n equals 1, actually one example of a planetary system, to many examples of planetary systems, we learn a lot. Can you imagine what will happen if we go from one example of life, ours, to many examples of life? That revolution of thinking, how we will think about ourselves, I can only imagine, right? Are we getting there soon? I don't know. But if we are in the next decade or so, it's because we're taking advantage of these observations, the various size distributions, the science that we're learning, and we're learning how to analyze them, the physical processes that are indicated here. I'm running out of time, so I'm not going to go into detail, but the physical processes that are indicated here, because we know from the absence of light, from shielding out the stellar light, we know that we can observe these planets, because most sun-like stars have at least one planet, and the nearest potentially habitable Earth-sized planet is likely orbiting a star within 10 light years, so not that far away on the scale of an astrophysicist. It's far away from McLean to DC or whatever my scale is every day, but there's many opportunities to discover, many opportunities for nature to really go out there and create an amazing environment that remains to be discovered. And it's going to be through these techniques and others that we yet have to invent at NASA and perhaps other places to really go see those worlds. So I hope you get the point. Kind of every once in a while, we learn a lot about nature, because of these eclipses. And it's right here, it's one of the most exciting phenomena. You should, the next eclipse is just around the corner in 3 years or so, 24, right? When is it, 24? 24. And it's, you want to go see that and go in the path of totality. But when you do it, remember that this very tool is one of the most important tools that really unlocks the knowledge of our universe around us and potentially helps us understand whether or not there's life elsewhere. Thanks so much.
Well, thank you. We have time for some questions and some answers. And in order to facilitate everybody being able to hear, including the people who are watching on the live stream, we have 2 runners with microphones. One has a microphone with a green top, and one has a microphone with a blue top. And when you get the microphone, please stand, tell us your name, and tell us if you're a member, and ask a question. Save the speeches for afterwards. Carl.
Carl Merrill, I'm a member. You showed those spikes that went up,
yeah.
and there's solar flares from that.
Yeah.
And the question is, they look pretty intense. Those planets you have are in the Goldilocks range, but those spikes could be severe enough that it would wipe out any kind of life that might be there. So I wanted to comment on that. And then one other comment, it has to do with something you didn't mention, and that is that I noticed in the paper the other day that the cosmic ray background in the solar system is increasing more rapidly than had been predicted, and I just wondered if you could comment on that.
Right. So you're exactly right on the first point. And actually, if you also read in the paper or read the news, actually in the last 2 weeks there was an analysis of one of those flares with planets there, and the calculation was actually really compelling. That says it would have wiped out anything. Right? The energy is so high that it's basically a blowtorch hitting the planet. And if there was anything in the history before, and very likely it wasn't, because that blowtorch isn't just coming once, right? It's coming multiple times. Yes, this actually matters. That tells us, right? The point you're making tells us that, hey, when we want to learn about life, we don't just have to learn about temperature. We have to learn about other effects in the solar system, including the activity of the star. There's many other things that the science community is starting to think about, including that, but many others too. You talked about the cosmic ray background increasing. We actually believe, so yes, it's absolutely true, the cosmic ray background is higher than it has been pretty much since the beginning of the space age. And the reason for that, there's another thing that is happening, which is that the magnetic field of the sun is the weakest that we've observed, in an epoch right now, since the beginning of the space age. Of course, it goes up and down, and it's a little bit, whenever there's activity, it's actually going up a little bit more. But we think that those two observations are related to each other. So basically what happens is the magnetic field that the sun ejects with the supersonic wind that it's blowing around the planets and beyond, that magnetic field is a little bit like a protection shield. And so if that magnetic field drops, the radiation that comes from galaxies, like from around the galaxy, from supernovas, from other places like that, that radiation is pushed back. And so basically if that push becomes weaker, the cosmic rays go up. So for those of us who'd like to travel in deep space, that's something that has to go into the calculation of health risk and other things. So it's a really important observation.
Okay, a couple of things. If you have a question, you have to hold your hand up long enough for somebody with a microphone to get to you. There are actually 3 microphones, green, blue, and red. And if you are watching the live stream, please ask your question using the comments box, and Ann will indicate to me if we have a question. So go ahead, Bob.
I'm Bob Hershey. I'm a member. What are the preparations for the 2024 eclipse that'll be a little bit different than previous ones based on what you know?
So it's funny, we just had the first meeting about it, literally 2 weeks ago. And we actually learned a lot. So you should know. So we spent a lot of time on this. Let me just tell you, I was wrong on this one. I joined NASA, and the team was working on this eclipse. I basically said, look, there's eclipses all the time. This is the scientist in me speaking. I'd never seen a total solar eclipse. I just told you how much it meant to me. Well, I didn't realize that emotional part of it. You don't read that in books. You have to see it yourself, right? And so I basically said, look, I mean, I don't understand why we're spending so much effort, time mostly. It's not so much money, but time on this. We have other things to do. And I basically said, look, I'll go with the team. Let's see what happens. Okay, so we actually spent a lot of effort. All the NASA centers were out there, including many libraries, many, the Challenger centers, many others were out there in partnership, which is along that track. And we actually did an analysis. We asked a university to actually assess what the fraction is of the population that in any way interacted with it, and the answer is north of 85%. So it is the most relevant kind of science event of this epoch, right? So it's kind of like 85% or more of adults basically said they were either there or interacted with content online or saw it and it meant something to them. So for me, I'm going to really pay attention, right? Because for me, this is like, and the one thing we learned, there's some lessons we learned, which is the only way we create the scale that we need is through partnership. So we want to start early. I think the opportunity also is to actually get communities involved that are not normally always addressed. I grew up in a town where I was one of the first students to go to university. I'm really always in tune with this. There's, intelligence is distributed not just in, next to top universities. It's just like, they're all over. There's great people, talented people all over of different gender, different origins. We have to go get them, show them that. It's these kind of moments that change lives. And so for me, we want to make sure that we do that. So that's one of the lessons we learned also. So many of the best examples were kind of reaching out, kind of in places where we wouldn't normally go. And then, of course, the trajectory is really different. So I think the other thing we want to do is start thinking about the science. What is really unique about the science? In this case, as I told you, it's the total duration of the eclipse. What will it be the next time? And I'm not equipped to talk about that yet. But it's these kind of, we want to take the lessons learned and really recognize that we have to put a lot more attention on it. I want to recognize I have to put more attention on it than I did the first time. We only were successful because of my team, not because of me. Yeah.
I think we have a question in the back there, the red microphone.
Yes, I'm Stuart Sweet. I'll be a member after I pay Robin my dues. My question is a little tangential to your talk, but you're a senior scientist from NASA, and I was just wondering if you would comment on a report that was, I believe was published in Nature, that is predicting we're about ready to enter a period of solar cooling, and that this is going to have a very dramatic impact on the debate on anthropogenic global warming. The paper is predicting that the output of the sun will fall by at least 50 years and perhaps cool our planet by 1 or 2 degrees, and therefore obviate the need to do much about global warming for the next century. I wonder if NASA is working on this issue, if it has formed an opinion, or if anyone's trying to confirm these findings. Thank you.
Thanks. Remember the question about the cosmic rays and the magnetic field? That actually is deeply related to the question you just asked. So yes, during the last 10 years, decades or so, both the magnetic field has been dropping, the ultraviolet output, so kind of the radiation that I showed you from the atmosphere, with these hotspots, has been dropping kind of in the single-digit %. But also the radiation, the visible output, the thing that actually is responsible for heating the planet, right, also has been dropping. I mean, a much lesser percentage, right? Kind of, it's really a fraction of a percent. So it's not a big drop, but there's a drop nonetheless. And so we know from history, from ice cores, and also in some of the cases actually from documented history that this is not the first time in humanity even that this kind of event can occur. We don't know how to make predictions in the future. The Nature paper that you saw, there's a group that basically says based on the analysis that we did and kind of based on the theoretical content, the knowledge that this team has, they think, hey, we're really going down that ramp, and it looks similar to some of these times that we may refer to as a little ice age in the past, the kind of, couple hundred years ago or so, right, in round numbers. And so at NASA, of course, we're very much responsible for many of the measurements that are very much used to document that. In fact, we just launched a couple months ago, 1.5 months ago, we launched an instrument that's now mounted on top of the space station that is taking over in the series of the total radiation measurements of the sun, and kind of from a series of measurements that we have done earlier, and really creating the time series that will be used to do the very model, the very kind of thought process that you're outlining. So what we're about in NASA, right, is very much providing the supporting data for these kind of considerations. I'm really glad we're not a policy shop, because I mean, I don't know how to do that, but yes, we think that there's tremendously exciting data, and data that has important impact, just like you outlined. I'm not standing here and I don't think we have a position on NASA exactly how we're interpreting these data, this paper as well as others that have said this thing or the opposite over the last few years. I think we just have to learn and kind of see as we go into this time whether or not what this paper predicts is happening, namely that the radiation is dropping, perhaps the magnetic field is dropping, and the cosmic rays are going up. Those are the very signatures that we see in our, not the radiation, we don't see those, but in the ice cores we see the impact of cosmic rays and spallation products from the atmospheres in the element of beryllium. Beryllium is depositing in snow layers, so we actually know how much cosmic rays there was as a function of time. So we know that during this period in the little ice age we actually had large cosmic rays. So we think it all hangs together just like you indicate. It's an interesting question. I don't know what's going to happen.
Bruce Murray has a question, I think. Is a red microphone coming, or a green one? Or maybe a blue one? Green one.
My name is Bruce Murray. I'm a member. I was very curious about the beginning of the lecture when you talked about how you were observing this thing from your airplane.
Yeah.
And you said that actually the airplane was keeping the telescope perfectly still. Could you elaborate on that a little bit? I'm trying to get my mind around what was happening there.
So I was talking about SOFIA. Remember, that's a 747 that had a telescope in the back. So basically, what we want to do with that telescope. So first of all, why are we doing it, right? So we want to take the telescope above the water in the atmosphere, or 95% of the water in the atmosphere, right? So we can look at emissions in the infrared in a way that we cannot from the ground. And we can actually, using the airplane, we can exchange the instruments that are behind that telescope to kind of keep up with innovation and kind of new technologies that are there. So the way this thing is flying, so imagine you want to look at a given direction, right? So the way this thing is flying, what I want to do when I want to observe this way is I have to fly, first of all, perpendicular to it, right? Because I need to look out the side, right? In many cases, depending on how high it is, I may be doing a really slow turn. And so basically what happens now, the point I was trying to make, what happens is using gyros, the very technologies that we're using on satellites, this telescope knows exactly where it is in the three-dimensional space, and the pilot has the information in the front to basically fly within the control envelope of these systems, so the gyros, the automatic system, the telescope can adjust for any, you've been in planes up there, right? For any bump, for any slight wiggle, the system can adjust. So that telescope never knew it moved around. The airplane, in that case, is really flying around the telescope. Because if you looked at it from the outside, the telescope is standing rock solid, looking at that place in the sky, and is controlling itself while the airplane is going up and down. But the pilot needs to, he can't take an arbitrary turn, because eventually the system runs out of play. Do you know what I mean? So that's what I meant to say. It's really the control system of the telescope is really the innovative piece here, other than the aerodynamics of making that airplane, with a hole in the back, which actually was a lot harder than people thought. But it's really that control system that makes it, that enables it.
And you're taking into account how the Earth is spinning
course.
at the same time?
Yes, absolutely. Yeah. So everything matters, right, in these kind of calculations. Everything matters, the Earth, the atmospheric drift, all these things. But the control system with the GPS, with everything, is basically, for all intents and purposes, this thing is standing still and looking at the star. Of course, it's never perfect, right? There's no such thing as a perfect experiment. But it's as perfect as we know how to do it.
Blue microphone. Name, member?
Thanks for the lecture, it's amazing. I just want to ask you a question about using the shadows to find this kind of stars. So there are older stars colder, and there are new stars forming in other galaxies. So are you more focused on the new stars, which are planet producing, and they have higher radiation than the one which is burnt out of fuel, right? So how are you able to predict, are you able to predict the age of the star by using this eclipse method?
So we look at the age of the star from the point of view of its radiation, right? Kind of over time, actually since kind of after World War II, there's some kind of really important work that happened with the understanding of how stars, kind of what the reactions are in the center of stars that what heats the stars, the nuclear reactions that are there, and how these nuclear reactions kind of occur in sequence. We know how to relate these reactions to the emissions on the outside and the age and mass of the star using the mechanisms, that we learn, kind of maps that we use, like diagrams, but also really learning about this. Some of these things we're really much more, we're really comfortable, we're really confident of, because we understand the sun so well now. We actually have understood it at the level that, again, when I was in grad school, I never thought we would. Because we're down to actually understanding the neutrinos that come out of it, that we observe totally independent observation. So we know about the age of the star because of its emission, not because of the planets, okay? Now, the interesting question is, so how do the planets factor in? What is the relationship of planets and the age and size of the stars? Remember, the only stars we're really observing are right in our galaxy right now. I mean, kind of we're not good enough to see beyond, right? I mean, kind of everything I'm talking about here is in our, cosmic neighborhood. And yes, a lot of the, actually, if you looked at the literature, you look at some of these news, you basically see that people are starting to really look at various classes of stars, and these red ones, we look at them as a class and kind of start arguing how the age of the stars, how the evolutionary process of the stars relate to the likelihood of some of these planetary systems to actually harbor life. So what you're talking about, the question you're asking, is right at the center of a lot of research that happens in this environment, both at universities, at NASA centers, and elsewhere. So it's really intriguing thing. Yes, the stars matter, but so do the planets. Yeah.
Oh, we have another question back there.
Yes.
Name? What's your name?
Hello, my name is Gabriel, and I am just here to learn.
A visitor.
Yes, lovely. So I am aware that there is a solar eclipse coming within the next 1 or 2 years that will start from the eastern coast of New Zealand and travel across towards the western coast of South America. Mm-hmm. And I was just wondering if you're going to install any telescopes or maybe possibly fly the 747, the SOFIA 747. I was just curious, with every solar or lunar eclipse that approaches as time comes by, will the SOFIA travel to every single eclipse that will be occurring, or does it depend on the geographical location?
So the solar eclipse that you're talking about, actually I want to tell you, basically every single solar eclipse in the last few decades, we've sent a NASA team there pretty much. And the reason for that is there's the research that's happening during eclipses is so profound, and so I don't know who it is, but I'm sure if I did just a little bit of work, I could tell you what the 3 groups are that are going. Now, I'm not aware of the fact that we will bring a plane in this case. So much of the solar eclipse observations can happen just the same way from the ground. Sometimes it's actually a lot more preferred. Frankly, the reason I was on the plane is we weren't sure it's going to be cloudy, right? So we have this 3-hour national broadcast on TV, and we didn't want to start with a dud, right? With a cloudy sky. So we basically took the airplane up. Of course, it didn't turn out to be needed, and you know, it was one of the most exciting experiences of my life. By the way, while we did that, we actually also brought some science instruments that are being analyzed. In fact, we just set up a talk at NASA headquarters for one of the instruments that actually found really exciting things. So I doubt we're going to bring the airplane. We might. I don't know. I can check into it, but I'm sure we're going to have observations there, because that the very tests that I told you, these space weather tests, are of course independent of geography. We can do them in South America the same way, because what we're interested in is the sun. And so kind of if we see the atmosphere of the sun, the corona, it's a good place for us. Cool.
Carrie, with the green microphone.
Carrie Liss, APL. I'm a member. So Thomas, I want your slides. It was a wonderful talk. And let me explain why. You probably want some of mine. I was in Carbondale, Illinois, and for my first total eclipse. And I brought my daughter there. And if you may or may not know, is that 7 years from now, they're going to have, 2024, we've been invited back because I gave a solar probe talk and they were so excited. They want to know what solar probe finds when they watch their next eclipse. So if you want to go to Carbondale, NASA is invited.
That's cool.
Secondly is I was in Patagonia. We got the long cord. I was freezing my arse off in the back of a pickup truck holding up a tarp while our telescope was getting bounced around by 40-mile-an-hour winds, and we managed to get the MU-69 occultation. We didn't even know at the time we got in the data because we were too busy just trying to shield the telescope. Awful point spread. We were bounced around all over the place. But that was a fantastic trip, and I don't know if you're interested in going to Senegal or Colombia. We have an August opportunity this year. And the third point I would make is that I agree, I don't want to live anywhere near an M-star. There's a lot of people who talk about M-stars the place to find the exoplanet because they're easy, they have big transits. They flare a lot, you're tidally locked. On the other hand, it's been pointed out in the astrobiology community, if you're 10 meters down under an ocean, the flare probably won't bother you. And if life formed at the bottom of the ocean, like the smokers, like we're thinking now, hot smokers, it could be, just like you're saying, maybe there is life there, but it's life not like we're used to, or it's evolved in a different way, because it could never get out onto the land like we did.
Yeah, couldn't have said it any better, and you can have the slides. Anybody can have the slides.
I didn't have to give that
Paid
speech.
for by taxpayers. Yeah, absolutely. Great comments. And of course, the point that you know, and I think most people in the room, is that actually, if we today, kind of the science community, like you and others, were basically talking about where else could there be life in the solar system, you know, like, it's not just Mars, which is what the analysis that I'm using here, kind of that thermal analysis would indicate. It's actually these really weird worlds out there around the giant planets, you know, Enceladus, Europa, Titan, you know, complicated chemistry. Really that interface between complicated chemistry, complex chemistry to biology, that interface, that's really a mystery to us now. There's a lot of research, including, you know, biology that's going on, synthetic biology and other disciplines like that. And kind of in astrophysics and planetary science, we're making contributions, but I mean, there's worlds out there that look in every way as promising as Mars, right? And so we can't wait to go back and look at them again. We discovered all these worlds basically with NASA spacecraft. Yeah.
I think that about wraps up the Q&A. So thank you, Thomas.
Thanks.
So before you go, I want to present you with a small token of thanks for giving the talk, which is a framed copy of the announcement of your lecture tonight.
Thank you so much. Appreciate it. Thank you so much. Appreciate it.
So before we close and adjourn to the social hour, there are, of course, a few housekeeping announcements. I want to thank all of our members and sponsors and supporters and those of you who came tonight. PSW depends on enthusiastic, active, and capable members and supporters and on our sponsors. Without all of you, we would not be able to continue and would not grow. You can apply for membership if you're not a member on our website at www.pswscience.org. It's really not very hard. You just get to the home page and you'll see this menu on the left, and you go down to, guess what, membership. And when you hit the membership button, you'll pull up an application for membership. Imagine that. And then you fill out the membership application and you get down to the bottom. And there'll be a submit sign. And if you don't submit it, well, we won't get it and we can't enter you into membership. When you hit the submit sign, you'll get to a payment page and you're going to have to pay the $75. If we don't admit you, we will refund the money, but that's pretty rare. So we suggest that you go ahead and submit. Now, you may get a lot of PayPal messages. PayPal is our merchant banking service that processes credit card payments. We use them not because we like PayPal or the PayPal mafia, but because they're inexpensive for nonprofits. So just ignore all the PayPal things and look for the little button that says, you know, pay by credit card or debit card. And push on that and you'll come up with the usual American Express, Discover, Visa, MasterCard. And you can pick whichever one you like and pay in the usual manner. And your application will go in. Give us the information that's asked for in the membership application. It really helps us to serve our members and to tell our membership about you when you're elected to membership. Where are we? Our next speaker. Oh, I should mention that PSW is a nonprofit educational organization. It's tax exempt under Section 501c3 of the Internal Revenue Code, and your contributions may or may not be tax deductible. Typically, they are tax deductible, but you should consult your accountant if you have one. And you should bear in mind that the new tax code may not make it as advantageous from a tax standpoint to make charitable donations, but it's the same to us, so please continue to give us money. Our next speaker will be Andrew H. Knoll. At the 2391st meeting that will take place on March 23rd, right here in the Powell Auditorium, the lecture will begin at 8 p.m. His lecture will be Life on Earth, the Deep History, and it will focus on identifying and study fossils that can constitute the remains of the earliest living things. When you read about this stuff in a textbook, it all seems very logical, but actually it's really, really hard to figure out what is a really old fossil of a living organism that had no bones and nothing solid and leaves unusual traces. And it's quite an interesting story as to what kinds of signatures you look for to convince yourself that what you're seeing in a 2 billion year old rock is actually a sign of something that was living that long ago. So I think it'll be a very interesting lecture. After Andrew, we have Don Norman. How many of you have heard of Don Norman? One person. Well, better than nothing. Well, Don Norman is a very well-known cognitive scientist. He leads the design lab at UC San Diego, where he's also emeritus professor of cognitive science. He's well known for several seminal books on design theory, especially his book called The Design of Everyday Things. Don was a vice president of Apple Computer, and he founded the Department of Cognitive Science at UCSD and served as its first chairman. He'll be speaking on democratizing design, and tried to parse out a way of describing what that might be. I think it's think of the internet of all things for everybody, designed to need and to task. April 20th, we have an invitation out, and we're hoping to hear back. Hopefully it'll be CubeSats, but we'll see. And then on May 4th, we have Thomas Budavari. He's a professor of applied mathematics and statistics at Johns Hopkins University. Tomas works on integrating very large, independently developed data sets, including large astronomical data sets. He's applying the statistical and computational methods that he developed for astronomy to the integration, analysis, and use of city data sets, such as water use, electrical consumption, road repair, demographic data, and the like, to develop more accurate and complete understanding of land use patterns to guide policy formation and implementation in our northern neighbor, Baltimore. On May 18th, we are working very hard to put together a program to talk about Cassini-Huygens and the really tremendous engineering achievement of that mission and the unprecedented, probably, treasure trove of data that it sent back from the Saturn system and what we've learned about it. one of which is, one item is that it is one of the most likely places in the universe, in the solar system, we'll find life. So I would urge you all to come and see that. Keep looking at the website for the complete program to be posted hopefully soon. Mark is smiling because he knows some of the vagaries of trying to put this program together that we recently experienced. And I think with that, we can bring the meeting to a close, so I will entertain a motion from a member to adjourn the meeting. Nobody? Carl, I have a second? Oh, wait, sorry. I forgot to mention that the social hour ends at 10:30, but after that, PSW members and their guests will meet across the street at the Fairfax Hotel Lounge, I think. Is it open? Okay, but we do meet over there? Okay, in the ballroom, just across Mass Avenue, and if you want to go talk to Robin Taylor or Lloyd Mitchell, wherever you are, or me. Now I will entertain a motion to adjourn. A second, all members in favor? All members opposed? We are adjourned to the social hour.